Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending this presentation on how plasma and flame surface treating improve adhesive bonding. Please note this webinar is being recorded, and you will be able to access both the recording and presentation slides once they are available online, usually within 24 hours. If you have questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the webinar. We'll reserve time at the end to answer as many questions as we can. Today's webinar is brought to you by Enercon Industries Corporation and Ellsworth Adhesives. Today we will cover adhesive basics, including the principles of successful bonding. We'll review different types of adhesives and the pros and cons of using them. We'll look at why surfaces need preparation for bonding. We'll take a look at different types of surface treatment technologies. We'll look at ways to measure the effectiveness of treatment, and we'll look at specific real-world applications. And of course, at the end, you'll have your chance to ask our expert panel your questions. Enercon is a global supplier of innovative surface treating technologies, including atmospheric plasma and flame surface treaters. These are designed to improve adhesion of adhesives, inks, paints, and coatings. Ellsworth is a global distributor of adhesives, sealants, tapes, and chemicals. Ellsworth owns many companies which specialize in related businesses, including custom packaging and custom resin formulation. Resin Labs is one of Ellsworth's subsidiaries and a co-sponsor of today's presentation. Resin Labs provides custom formulations of epoxies, urethanes, and silicones. Joining us today is Greg Kennard, Senior Chemist at Resin Labs. He holds a master's degree in chemistry from the University of Illinois Urbana-Champaign and an MBA from Marquette University. He has been working in the coatings, printing, and adhesives industry for the past 24 years, working for Valspar, PPG, Johnson Polymer, Serigraph, and Resin Lab. Also with us today is Wilson Lee, Enercon's Business Development Director. Wilson has extensive experience in surface treating applications over a wide variety of industries. Wilson works with Enercon customers on developing plasma and flame technology solutions to solve their surface treating challenges. Wilson earned an electrical engineering degree and an MBA from Clemson University. With that, we'll start the presentation, beginning with Greg.
All right, some adhesion basics. Let's start the presentation by talking about substrate wetting. Substrate wetting is critical in order for any adhesive to bond to any substrate. Without it, you won't get a good bond. The image on the slide demonstrates what pore wetting would look like. On the left-hand side of the image, you can see the adhesive or coating, whatever you're working with, balled up. That's the blue image. And then the substrate would be the yellow image. This would be similar to water on a Teflon coating in your house. If you ever put water in a frying pan, it beads up. It doesn't let the frying pan out. Obviously, as you shift left to right, you see better wetting. The far right image shows excellent wetting where the surface or the bond angle has decreased and the material is wetting out the substrate quite well. What can cause poor wetting? Well, substrate issues can be, not necessarily issues, but substrates can be part of the problem. You have low surface energy substrates like polyethylene or polypropylene that are very difficult to bond to for many materials. You can also have issues on substrates that aren't as difficult to bond to, such as a mold release agent that might be present on the surface. The panels may have been handled, so you might have skin oils that have been put on the surface of the substrate. You can also have debris or dust on the surface, which will disrupt adhesion as well. In order to get bonding or adhesion to a substrate, you need bonding. There's two, we'll talk about basically covalent bonding, which is very high bond strength materials if you can get covalent bonds. This is an actual reaction that occurs between the adhesive and the substrate. Some common ways to accomplish this for formulators of adhesives and coatings is to use organosilanes in a material, where the organosilane will react with the hydroxyl functionality on the substrate, assuming there's hydroxyls present, and the other portion of the organosilane will bond into your adhesive or your coating. Polyurethanes also offer some of this. The isocyanates used to cure up the polyurethane adhesive will also bond with hydroxyls on the surface of a substrate. There are other types of chemistries that can do this as well. Some other bond forces that you will run into, which are lower in strength, include van der Waals forces and hydrogen bonding forces. These are lower in strength, but you get many of them across the surface of the substrate, so you can still get a good adhesive bond. But these are the weaker forces that are present when dealing with most plastics. There are several theories of adhesion, one of which is the mechanical theory of adhesion. This theory looked at adhesion as the material that you're applying, your adhesive or your coating, diving into your substrate, into the pores of the substrate, into the valleys of the substrate, and upon curing, they literally form anchors into the substrate, like the roots of a tree, for instance. That doesn't really account for the chemistry that you're working with or wetting or anything of that nature. Adsorption and chemabsorption theories. The adsorption theory looked at substrate wetting. So the wetting concept that I just discussed was discussed in the adsorption theory, where wetting is critical in order to get adhesion. But the adsorption theory did not account for chemical compatibility between your adhesive and your substrate. The chemabsorption theory does bring in chemical compatibility as well as substrate wetting. The diffusion theory is a theory that's based on chain entanglement. So this would apply to plastics, for instance, where your substrate is made of polymeric chains, as is your adhesive, and the adhesive polymeric chains literally dive into the plastic substrate, and you get entanglement between the polymeric materials of the substrate and the polymeric materials of the adhesive. There are things that can be done in formulations to help with this. For instance, solvents will help bite into the substrate and allow for better chain entanglement. Fusion of plastics is sort of an example of that. Electrostatic theory looks at charge alignment between the substrate and the adhesive. So there are temporary charges that will occur in a polymeric chain as well as in the substrate if there's polymeric chains in the substrate. And these will align themselves in a certain order to give some adhesion characteristics as well. When talking about adhesion, and in particular if you're talking about the failure of an adhesive, it's important to recognize the difference between adhesive failure and cohesive failure. Adhesive failure is the failure between the adhesive and the substrate that the adhesive is bonded to, whereas cohesive failure is actually failure within the adhesive itself, where the adhesive breaks apart. In the case of cohesive failure, it means that your bond strength between your substrate and your adhesive was actually greater than the bond strength of the adhesive to itself. That's generally the preferred method of failure. If you're going to see failure, you want to see it in cohesively, but this assumes that you've selected an adhesive that's got a strong enough bond in the first place to the substrate that you're working with. Some other things that you need to consider. Surface roughness and surface area. The van der Waals forces that we were talking about when discussing plastics require contact between the adhesive and the substrate. If you have greater surface area, so say for instance you're working with a plastic that has a texture molded on the surface, that texture actually increases the surface area of that substrate versus having a very smooth substrate. That increased surface area will give you more bonding sites, which can help promote adhesion. Surface roughness, which you might get by actually abrading the surface of the substrate, also helps. This gives you greater surface area, but it also gives you areas for additional mechanical bonding where your material might dive into the substrate better. Solvent attack is an important thing to recognize. Solvents can be used to actually promote adhesion. So it's not uncommon at all to have a solvent like N-methylpyrrolidone added to a formulation in order to have it bite into the substrate and actually create a better bond to the substrate. Solvents can also be used to clean plastics if you're working with plastics. The important thing to note there is you need to pick your solvent wisely, because solvents will also attack the plastic and craze the surface, and they can cause it to have a dull finish, for instance. Heat is an important aspect when thinking about adhesion. If you use heat to cure your adhesive, it frequently will end up with a higher bond strength because you drive the reaction of the adhesive further than it might have been driven under ambient conditions. Heat can also help with substrate issues. For instance, crystallinity and nonpolar substrates can be improved by heat. Heat can also give you better diffusion. So when you have additional heat for the curing process, the polymeric substrate will move, the polymer chains will move on a microscopic level, and the adhesive will move as well, and it'll have a better chance of binding into the substrate. Heat is another thing to consider, though, when thinking about service temperature. If you have a high service temperature for your application, the adhesive you choose needs to be able to bond at that high temperature. Glass transition temperatures are important because they are related to your adhesive. All adhesives will have a glass transition temperature, and that temperature is the point at which the material goes from a glassy state to an amorphous state. So it goes from a rigid solid to a material that's more flexible. It's analogous to melting, but polymers that have been cross-linked don't melt. They actually just have this transition instead. If you're dealing with a high service temperature and you have an adhesive where you move through the glass transition temperature in your application, it's important to evaluate the adhesive at that elevated temperature to make sure that you still retain your bond, because a lot of materials will start to have lower bonds as the temperature is increased. Coefficient of thermal expansion is an important concept, particularly when dealing with the bonding of two substrates that are different from one another. An example of this would be if you're bonding a metal to plastic. The metal will have a low coefficient of thermal expansion, whereas the plastic will have a significantly higher value for coefficient of thermal expansion. When you're dealing with in real-world use and you've got temperature fluctuations, these differences in coefficient of thermal expansion can cause the adhesive, the materials to delaminate from one another. To avoid this, it's very common to use materials that actually aren't quite as hard and are a little more flexible to accommodate these differences in coefficient of thermal expansion. I've already mentioned crystallinity of nonpolar substrates. The last thing to consider would be plastic stresses. When you have a molded part, stresses are molded into that plastic based on heating and cooling of the substrate. When you do things like a thermal cycling test, for instance, those stresses that are inside that plastic can cause the plastic to deform, and those stresses then can help create areas where you have bond failure. There are many different test methods for testing how strong a bond you have. A common one that we run at Resin Lab is lap shear strength. The image on the right shows how lap shear strength is tested. You have two pieces of plastic, in this case that's high density polyethylene. You overlap a region on the two pieces of plastic. You have adhesive between them, you cure it up, then you put them in the jaws of a universal tester, and you use the universal tester to provide quantitative data for how strong that bond might be. Peel tests also use a universal tester. The test is set up a little differently. You might do a 90-degree peel test of two different materials, or a 180-degree peel test as well. There are many different tape tests where you have a material on a substrate and you typically will crosshatch it. There are tools that are designed for creating very even crosshatch patterns. Alternatively, many people will just use a razor blade and cut into it, or they might cut an X into it. And then you apply the tape over the surface and you rip the tape off to see whether or not the material is removed from your substrate. There's many different types of tapes with varying strengths, so it's important to make sure that you're consistent in how you do your tape tests. Direct tensile testing involves bonding something to your actual material, or depending on the parts that you're bonding together, you might be able to literally put your part into the jaws of a universal tester so you can tear it apart directly, which would be a direct tensile test. Impact tests involve dropping weights onto your part. So a lot of times it's big steel balls. In the coatings industry, they use impact testers. And the testing can be done directly, where you directly impact the top surface where the adhesive or coating might be. And an indirect test would be where you'll hit the piece from the back side instead. Then you look to see whether or not you lose adhesion. Chip testing involves placing your substrate or your coating into a device where you can rotate the device with whatever medium you're using to do the chipping. You might be using rocks, you might be using ball bearings, which you literally just roll it across the surface of your piece repetitively to see what kind of chipping you might get. Thermal cycle testing involves going from cold to warm temperatures and then warm back down to cold temperatures, which causes deformation frequently in the parts. You get shrinking, contraction and expansion, and differences in these can cause adhesion failure that you do not see under ambient conditions. There are many, many other methods. This is just a short list of different test methods. All right, let's discuss some of the types of adhesives you might be familiar with or could use. Epoxies are the workhorse of the adhesive industry. They are used in many, many different applications. The reason for this is they give you very high bond strengths, and they're also very durable. They have high temperature resistance, so you can use these in applications where you have a high surface temperature. They also give you very good solvent resistance. They come in a wide range of properties. You could have a low viscosity material, a high viscosity material, slow curing material, faster for an epoxy. They offer excellent adhesion to metals, glass, and wood. And they generally have very long shelf lives at room temperature as well. There are disadvantages. They are used in the plastics industry, but they don't generally bond as well to plastic as some of the other adhesive choices. They're usually harder and less flexible, so they can cause you issues where you have two different substrates with different CTE values. And in that case, you may not want to use an epoxy. You may want to look for a specially designed epoxy. They will discolor if you're using them. If they're clear, you'll see them, they turn yellow with time, with UV resistance. They do that with heat as well. And they generally are slower curing than some of the other technologies. A polyurethane is another choice. These offer very good adhesion to plastics and are very commonly used on plastics. They also offer good adhesion to other substrates like metals. The cure speed can easily be adjusted, which offers advantages in application method. They tend to be more flexible, less rigid, so they're a better material frequently for CTE mismatches between substrates. They have good low temperature properties, once again because of the flexibility, and they tend to be lower in cost. However, a major disadvantage of a polyurethane is they are sensitive to moisture and humidity. If you have a substrate that inherently has water in it, it is not usually a good choice for, at least for a two-component polyurethane adhesive. They will form bubbles inside your material. In fact, if there's enough water present, they'll foam right up. This is one of the ways they actually make blown foams. Another issue with polyurethanes is they have limited thermal stability. If you have a service temperature requirement above about 125 degrees Celsius, a polyurethane is probably not a good choice. But if you're at 125 or below, you're in good shape. They're not recommended for substrates like wood or paper because they have moisture present. Acrylics have a major advantage in that they require little to no surface preparation. They're also very fast curing, and they offer excellent bond strengths to many substrates, including plastics. Some disadvantages would include they're not very good for bonding wood, concrete, or flexible rubbers. They generally have a strong odor. They're flammable. They don't have they have lower high temperature limits than an epoxy, although they would be higher than a polyurethane. And they typically require refrigerated storage. Cyanoacrylates use moisture to cure. A common example that you might all be familiar with is superglue. Superglue is based on a cyanoacrylate technology. That has a very fast cure speed, and they give you very good bond strengths to a number of things, including plastics. Some disadvantages: once you open up the container, these have shorter storage lives because moisture will get into them typically when you start opening containers unless you're careful. They have odor, and they can cause sensitization in an industrial setting. They're not very good for wood or paper products. Once they're cured, they actually don't provide you very good moisture resistance, and they actually require a thin film in order to get that fast cure. If you've ever worked with super glue at home, if you have a thick bead, that actually doesn't cure very quickly. But if you've ever put a bead between your fingers and squeeze your fingers together so it's a thin film, it bonds very quickly. Hot melt adhesives are actually thermoplastic adhesives, and they literally melt with heat. They come in with many different chemistries. You might have ethylene vinyl acetate, thermoplastic polyurethane, a variety of different chemistries. These generally contain no VCs. They have very long shelf lives. They're good for wood and paper, and a common application for them would be a glue gun. If you've ever used a glue gun around the house, you were using a hot melt adhesive. There are disadvantages. They have limited heat resistance. They melt when they get to the temperature they're designed to melt at. So as you start to get warmed up, they're not going to bond as well. They provide limited chemical resistance, and they provide limited adhesion. Two basically specialty adhesives, anaerobic adhesives, they require an absence of air in order to cure, and they require contact with a metal. There's only so many applications that are like that, but one of the very large applications that you will find them in is thread lockers, where you lock the nut onto a bolt. They're also used in retaining compounds. Polysulfides have they're largely used to fuel or to seal fuel tanks, and this is because they have very good chemical resistance and they bond well to metals. Silicones are not structural adhesives, but they still get used where adhesion is necessary. They have advantages. They're highly flexible, including at very low temperatures. So they are good materials when working with CTE mismatches. They have excellent resistance to very high temperatures. So they are kind of a go-to material when very high temperatures are required, but super high bond strengths aren't required. They're easily adjusted in terms of cure speed, and another big advantage is they have a very low toxicity profile. The disadvantages, they do not provide the kinds of bond strength structural adhesives provide. They tend to be expensive, and they only provide moderate chemical resistance. Okay, you might find adhesives also described in another manner. Someone might say, I'm using a solvent-based adhesive. Well, what that means is that solvent is the carrier for the adhesive, but many different chemistries can actually be put into solvent. Some common ones would be an epoxy, could be made as a solvent-based epoxy, or it could be 100% solids. It can also be a water-based epoxy, which we'll talk about in a second. Urethanes also can go into solvent readily. So there's many different chemistries that you might find that are actually solvent-based adhesives. They typically will have lower viscosity and they flow well, which opens up your application methods. You might find these spray applied, for instance, where 100% solids material might be more difficult to spray. The solvent has an advantage in that it can help promote adhesion to plastics. That's because the solvents that are present can actually bite into the surface of the plastic and promote the adhesion. However, when you're curing these systems, the solvent does need to evaporate. So you may want to use ovens to expedite the evaporation process. Because you have solvents present, you have volatile organic compounds. So you have to deal with possibly regulatory issues related to that. Shrinkage is common because you have solvent that has to leave the system. So it's going to cause shrinkage of the material. And because solvents are present, you have flammability issues. Waterborne adhesives use water as a carrier. There actually still is solvent present. They're called co-solvents. This type of adhesive can also be done with many different chemistries, including epoxies, and they actually do have waterborne polyurethanes. They're lower in VOC, and that's because water is not a VOC, but the co-solvents present generally are, unless you're using one that's exempt. These are excellent for bonding wood and paper. They can also be used on many other substrates. However, they tend to have more issues with some of the other substrates. Wetting can be an issue. That's because water has a surface tension of 72 Dyne. So if you're bonding to plastic, for instance, that's much higher than the surface tension of plastics. So you need to use additives or your co-solvent package to make sure that you get the surface tension of your material low enough to wet out the substrate. They generally have less chemical resistance than their solvent-borne counterparts, generally have a little lower adhesion, and shrinkage is still an issue. UV adhesives come in many different chemistries as well. You can have epoxies, urethanes, acrylics, polyesters, and they all will have acrylate functionality present on them to allow for the reaction. These cure on demand with light and provide an instant cure. They're VOC free. They do bond well to metals and plastics. They tend to be expensive. They tend to have odor. You do need to be careful in terms of the type of application. If you're using it as an adhesive, you need to have an one of your substrates needs to allow the light to shine through it to cure the adhesive. They can also have stability issues if they're exposed to light in the container for storage and whatnot.
All right, thanks, Greg. Very insightful information on adhesion basics and types of adhesives. Wilson, we're going to switch over now to look at how surface treating technology can help adhesives bonding performance.
Okay. All right. Now that we know a little bit more about adhesives, let's talk about issues that you might see that would cause poor bonds, even though you might be choosing the correct adhesive. Impediments to adhesion. Many of these things that you'll list here: low surface tension, formulations that include components that migrate, fluoropolymers come to mind. Mold release can cause issues with adhesion, low temperature UV, stresses, design and fabrication issues. All of these can be issues in your bond. So the surface of the material that you're trying to bond is critical, as mentioned before, and we're going to look at those in the next two slides. If you have a hydrophobic surface, you have low surface energy. You might have contaminants on it. There may be migrating additives such as flame retardancy materials that are put into the resin. You might have fluoropolymers in there that like to switch positions on you during, just during the life of the material, and these cause limited bonding sites, and you're going to have a poor bond. If you go to the next slide, hydrophilic surface has high surface energy. You generally remove the surface contamination so that you're not bonding to the contamination, you're bonding to the material itself. You've either removed or you've done something to affect the migrating additives, and that's increasing your bond sites and giving you a much higher surface energy and a better bond. When we work with new customers, generally speaking, these are the types of alternatives they have to get a good bond. When I'm looking at a new application, it's almost always they're currently using a primer or some sort of chemical etch or solvent. They may be using mechanical methods like sandblasting. Very rarely they're using a vacuum plasma. And then, of course, what we do is the atmospheric and flame plasma. All of them have their own advantages and disadvantages. The biggest advantage to atmospheric plasma and flame is the through cost, or the consumables, are very, very low, and the equipment cost is not as exorbitant as vacuum plasmas, and you don't have the issues that you have when you're having to get rid of solvents or primers or other nasty alkaline materials that might be used in etching. So inline plasma and flame treating. What is plasma? Plasma is the fourth state of matter. Solid, liquid, gas, plasma. Plasma is just ionized gas. You see it naturally in the northern lights, aurora borealis. Lightning is many times considered a plasma when it's actually the air around the lightning strike that gets ionized that creates the plasma. We use a high voltage arc to create our plasma. So we have three different types. We have the blown ion plasma that you see there, which is a line of sight direct type of surface, or excuse me, a direct type of discharge. We have the blown arc plasma, which is similar to a blown corona. It has a wider nozzle. It can go out to 2 or 3 inches. The speeds have to be a little bit lower. It doesn't do quite as well with the cleaning as the blown ion or the flame of the surface, but there's a lot of applications, especially print applications, where blown arc is a good alternative. And then, of course, flame. There's some advantages to flame over the blown ion in that you don't have to be quite as close to the surface to get a good treatment. Some parts that have more 3D type applications to them, you might want to use a flame because you're going to have different distances. When you're dealing with a blown ion type application, you need to be concerned about the distance that you are from the substrate at all times. Flame is a little more flexible in that, but of course, there are other advantages and disadvantages to both, but we can help you pick which one would be the right application. This is a little slide that kind of goes through what happens when you treat a surface. This is the cleaning step. So basically, you're going to do three things. First is cleaning. So you have contamination on the surface, and the plasma or the flame will clean that off, whether it's organic, and many inorganic impurities can be removed. This is done by first taking all the static off the surface, so anything being held on by static gets removed, and then it will clean the other impurities off of there as well. Not all impurities, but most. The second thing it does is microetching. This was mentioned earlier by Greg about giving more bonding sites. So on the left here side, you have minimal surface area, and after you've treated the surface, you can see that you've got much more surface area with which to bond. So if you've got adhesive there, it gives it more bonding sites. And the third is functionalization, and that is where we're actually changing the surface and adding groups, hydroxyl groups, carboxyl groups, oxygen groups to the surface, which actually does the increase of the surface energy so that you have better bonding sites. This is a picture to show a PE film, the original film on the left, of course, and then after it's treated with plasma, you can see that it's roughed on the edges over there, and again, you're increasing the surface energy, giving yourself more bond sites. This could be ink, it could be water, it could be anything, it could be adhesive. You've got the untreated surface down below. You could also say that that was a treated surface. When you ran next to the windshield of your car, what you're doing is you're decreasing the surface energy so that the adhesive bonds between the water molecules are stronger than the bond between the water and the surface. So that water will bead up like that and it rolls off. When we treat a surface, you're increasing the surface energy so that the water, the ink, the adhesive will all wet out. And in the printing application, the picture of the dog over there, you can see that if you're using adhesive, you want a nice surface, active surface in order to allow that picture to stay on there and you won't be able to remove it or scratch it off like you would if it was an untreated surface. Types of plasma treaters. We have three. Air plasma. This is using compressed air and a high voltage arc. So the cost of operating a single jet in this application is somewhere around 10 to 20 cents per hour. So that's when I mentioned that's a low consumable cost. That's a couple of dollars a day. You can operate these methods. Basically, you're running compressed air past a high voltage arc. There's a little more to it than that, but that is creating the ionized gas that's going to react with your surface, give you the bonding sites that you need, cleaning the surface, and then functionalizing the surface. Flame plasma, again, you're adding different functional groups to the surface, but in general, you're getting similar applications or you're getting similar results in increased surface energy onto the surface, but you have more flexibility in the size that you can cover. And when you have an odd-shaped application like the dashboard that you see on the right-hand side, which obviously has many different levels, it is easier to treat that with a flame because you do not have to be quite as precise with the distance that you are from the flame to get an increased amount of surface energy. And then we have some variable chemistry plasma. This is where we're using different gases, such as maybe a forming gas or a nitrogen, to get different surface properties on there. There's various reasons why you might need to do that. 90+% of the applications are all going to be air plasma, but there are certain cases where oxides on the surface, for instance, with aluminum sometimes or copper, you might not want the oxides on the surface, so you may treat it with a different type of gas. There's also other advantages to things like nitrogen. Nitrogen actually burns hotter in our chambers, but the discharge is for longer, so that I can actually treat some materials from a greater distance and get the same or improved surface energy changes. How do we determine the effectiveness of the treatment? Here are some common methods. Dyne pens tape test, peel test, lap shear, and contact angle. And this goes through the cost of these individual methods, if it's objective or subjective, destructive, where it happens, and the ease of use. Most often we're using Dyne or contact angle to measure the surface energy. Those are good indicators of adhesion. They are not perfect indicators of adhesion. There are a number of materials out there that actually, with a higher contact angle, I should say, or a lower Dyne, actually bond better. So again, this is a good method, but what this does is help us understand what we're doing to the surface. I personally prefer contact angle. It's a little bit less subjective than Dyne. There's some devices that make it very easy to do on the on the manufacturing floor. So if you need to test during your process, it's very, very easy to do that. Here's some pictures of those surfaces that we were talking about, or the methods. On the top, you can see the Dyne pens, and then on the right there, you see Dyne ink, used either with a pen or with the ink. And what you do is you run a line across the surface, and if it starts to bead up, like it does here in the incorrect Dyne level, so let's say you're using 50 Dyne in this example. Well, at 50 Dyne going across there, that would be a fail. So that means that your Dyne is actually lower than that. If you did 50 Dyne and you got the second trail there and it stayed together for 2 seconds, then you would have said to have passed it at 50 Dyne. So now you know that your surface energy is above 50 Dyne. Contact angle is inversely proportional to Dyne, and it varies by surface. So I can't just give you one graph that shows you what, if you're at so-and-so Dyne, you're at this level of contact angle. But on the left-hand side there where the contact angle, you see a hydrophobic material that's got about a 90-degree contact angle. That's a pre-treatment. And then on the right side there, after treatment, you've probably got about a 35 or 45-degree contact angle. Again, you've got better wettability there. You're going to have higher surface energy and better bonding sites. This slide is a little complicated. Pick any material, say polypropylene, and it has a surface energy prior to any treatment of approximately 30 Dyne. And then you go to the right-hand side and you pick maybe a UV adhesive. Well, a UV adhesive recommends that you need at least 45 Dyne in order to get a good bond onto anything. So if you're at 30 Dyne with polypropylene and you need at least 45, we need to increase that surface energy. And a good rule of thumb is to increase the surface energy by 10 Dyne or so. So in this case, we might want to increase that polypropylene from a 30 to maybe a 55 Dyne in order to achieve good bonding. Here are some examples of materials on the next 2 slides. Their initial Dyne is listed there in the middle. Teak, for instance, starts out at about a 30 Dyne level. On the right, you're going to see a range of post-treatment levels. We can vary these levels based on the speed and the distance and the way we treat it, whether it's going to be flame or blown ion or blown arc. Here's some more polycarbonate. Polycarbonate is one of those odd materials that in certain applications you actually get a better bond at a little bit lower Dyne level. And PTFE is always hard to treat. You can get the post-treatment up to about 50, but anytime you have a fluoropolymer, you're going to have issues. The timing of it is such that the treatment doesn't last very long. And we'll discuss that here on the next slide, I believe. Oh, nope, 2 slides, I apologize. This is showing a PE cured with a UV cured adhesive, tested after 24 hours, and you can see the control there, and then we treated with blown ion and blown arc, and we were able to increase the bond strength by a little over three times. So how do you determine the treatment effectiveness? Well, I mentioned that Dyne and contact angle are good indicators of adhesive, but they're not perfect. We need to run the test. So we generally have a 2-step system when we're looking at application. The one is proof of concept. Does it work? Can we increase your surface energy with whichever method we choose in order to improve your process and get you the results that you're looking for? The second part of that is dialing it in to meet your specific needs. I may be able to take a contact angle from 90 down to 20, and give us a nice wet surface, wettable surface with high surface energy, but you may not need to be down at 20 to get the bond that you're looking for. So we'll work with you to figure out what contact angle or what Dyne level you need to be at in order to successfully repeat your process and get a good bond each and every time. So where I said it once earlier, and I'll say it again, that Dyne and contact angle are good indicators of successful adhesion, but they're not perfect. And you shouldn't use that as a perfect measure. Now, if you have the same process before and after, then you can say that Dyne or contact angle is going to be a good indicator. But anytime any of those processes change, all bets are off. How long does treatment last? This is one question that I guess ask all the time, and the variables on the right that you see all affect the Dyne levels and make them go down. Each material has a different life. Basically, you'll treat something, you'll go from a low Dyne to a high Dyne. It'll have a steady state time, I call T, and that could be anywhere from a few seconds to a few days to a few months, depending on the material and then how it's stored. Then it's going to generally go back down. So, for instance, let's say we started with a material that was at 30 Dyne and I treated it with a blown ion and it went up to 60 Dyne. It may stay at 60 Dyne for 12 hours and then it's going to start to fall off. It usually never gets back to its original steady state of 30 Dyne, but it will fall off at some point. And that's why we need to work together to try to figure out, okay, I need to be at above 55 Dyne in order to have a good bond. So we'll treat it to a certain level and let you know, okay, I need to do my next step within so many minutes or seconds or hours from the pre-treatment in order to, again, make sure that you get the best bond that you have. Applications.
All right. I think, Greg, you're going to walk us through this first case study.
Yep, a couple of case studies. This first case study involved high-density polyethylene as a substrate. The adhesive that was being evaluated was Resin Labs UR 7001 Clear. This is a 100% solids 2-component polyurethane adhesive. Substrate treatments. One of the substrates was abraded in methyl ethyl ketone white. So we have an abrasion, so we're roughing up the surface and we're increasing the surface area. And methyl ethyl ketone will actually attack a substrate and make it a little easier to bond to. Another treatment involved flame plasma treatment. In this case, there was no abrasion or solvent wipe on the panel. The only thing that was done was the flame plasma, and we also did a blown arc plasma treatment where, once again, there was no abrasion or solvent wipe. Before treatment, the substrate had a Dyne level of 33. After treatment, we had a Dyne level of 60 in both cases. The test that was done is a 1-inch by 4-inch overlap of the lap shear coupons, and the adhesive was applied within 45 minutes of the treatment of the substrate. The material was allowed to cure for 24 hours under ambient temperatures, and you can see that the abraded and MEK white polyethylene gave a 120 psi bond strength. Flame plasma increased this to 443 psi. And blown arc plasma increased it to 393 psi. A second case study involved the use of polymethyl methacrylate being bonded to aluminum. So here we have two different substrates being bonded that have different coefficient of thermal expansion. The adhesive that was used is Resin Lab RX 160818. This was a platinum cured silicone. This is a soft non-structural gel. So this is not intended to be a structural adhesive. It was chosen because the two substrates have different CTEs, and for this customer, it was allowing them to get where they needed to go. The substrate treatments. All the substrates were IPA wiped. IPA is not aggressive solvent. It's used frequently to clean plastics off. It doesn't really promote bonding. Only the PMMA, so the polymethyl methacrylate, received any additional treatment. The control in this case had no additional treatment on the polymethyl methacrylate, and then once again we did blown arc plasma and flame plasma. Before treatment, the PMMA had a surface tension of 31, and after treatment you can see that flame and blown arc both took it up to 60 again. Same test method, 1-inch by 4-inch coupons, 1-inch by 1/2-inch overlap area. In this case, the adhesive was applied within 2 hours of the treatment, and the adhesive was allowed to cure for 4 to 8 hours before testing. Without any treatment, we only had a bond strength of 21 psi. With flame plasma, this was increased to 100 psi, so almost a 5-fold increase, and blown arc plasma increased it to 88 psi.
So Wilson, you're going to talk a little bit now about from lab to applications in the field.
Yeah, we're going to go through these slides relatively quickly just to show you some of the applications that we've worked on in the past. Injection molded parts are always good for either a blown ion plasma or a blown arc plasma. You'll see a lot of this in automotive and then just general consumer products. The next one is one of the original automotive applications for plasma. Older cars had a terrible time keeping the water out of headlamp assemblies, and now we've pretty much eliminated that. We treat the housing prior to the silicone adhesive that's put in there, and then the lens is put on, and we have a nice seal now, and it's usually pre-treated with a blown ion system. Spoiler assemblies is another. If your car has a spoiler on the back or you see them, it's usually polycarbonate plus ABS. You're usually treating it with either a flame or a blown ion. In the picture in the middle, you can see the plasma jet or blown ion jet, and then right behind it, the dark tube is the adhesive being applied. So you can just follow the blown arc with the adhesive and apply it right in line for a quick application. The interior panels of your car, we mentioned the dashboard earlier, but all interior panels are generally a fiberglass or polypropylene of some sort, and you can treat that with either a blown ion or a flame, depending on the size of the part. Increase that surface energy right before the decorative portions of the car are put in there so that the interior looks nice. Again, flame plasma is a general application for this. Door gaskets, all the gaskets you see in your car, prior to using flame, they would generally use a solvent wipe and then a primer, but you can achieve better bonding and eliminate the primer and the solvent wipe by just using a blown ion onto the surface where you're going to put the adhesive in the gasket. Folding cartons is another application. You're treating the bond line, the glue lines of the carton. Depending on the material that they're using, they'll use different adhesives on these cartons, and occasionally there'll be a little bit of an issue with the material and the printing on the material, so it helps the bond if you use a blown ion to treat the bond lines. Potting applications, filling in some of these electrical components, that's generally done with a blown ion. It could also be done with a flame. The reason we were able to do this on like a PCB or electrical component is there's very little potential to arc to the surface and damage the PCB board, especially with a blown ion. So you can get a good clean surface there in order to pot that application. Window and doors is another application. We're generally bonding the frame together in some sort of manner. It's a good application depending on the complexity of the surface for either a blown ion or a flame. Both would work well. There even could be some applications where a blown arc might work in this situation. This is a painting application. Initial dyne was less than 30. We had a final dyne here of 58. I imagine they used either blown ion or flame in any of these applications. Again, you're going to look at that depending on the material. You're going to look at the size and how many different dimensions that we need to try to cover and what is the most effective way to get the treatment. Here's another window and door assembly that you can see, and there's some bonding. We've already done this one, so we don't have to really concentrate on that one. And then bonding composite door skins together, another window and door application. This was probably a flame-treated application where we increased the dyne from 40 to 70 to get a better bond between the skins. PVC door, wood veneer to a PVC door. They're almost always pre-treated with flame in order to increase that dyne so that you can get, again, the coating, and it'll stay, and it'll, a long-lasting coating of the veneer. And then assembly applications, this is just showing a foam filled construction in order to make sure that we have a good bond on the outside, and that stays on the outside. Is usually a flame treat prior to the coating going on.
All right, thank you, Wilson. Thank you, Greg. Before we get to our review and our question-answer session, we're just going to throw a quick poll question out to our audience, and I'm going to launch that here momentarily. All right, we've sent that poll out to you. If you could give us your response, we'll wait for you guys to answer, and then we will move on to the review and the question-answer session. Again, you can use the GoToWebinar tool to provide any questions that you have for our expert panel today. Looks like we've got about 30% of the responses in. We'll give you a few more minutes or seconds to do that. And we'll give about 30 more seconds. And looks like we've got just about everybody here. So we're going to close that poll, and we're going to move on to our review. So we learned today that adhesive must wet out the substrate to achieve proper adhesion. We've looked at the importance of making sure you have the right adhesive chemistry that's going to work well with the specific substrates that you are going to be bonding to. We looked at the specific characteristics adhesives need to have required for the ultimate application of the adhesive. We've seen from the surface treating side of things how plasma and flame treaters can clean, etch, and functionalize surfaces to improve their adhesion properties. We've learned that dyne levels and contact angles are indicators of adhesion success. We also looked at many applications and found that treatment is most often installed in line prior to the bonding application and can be integrated with robotics, indexing systems, or conveyors. With that, we'll begin opening up to the questions. And the first question we have here is for Wilson. What's the best way to determine if plasma or flame is best for a particular application?
Okay, there's a lot of things that you have to consider. First, the material, then the speed and the size of the area that you want to bond. If I'm looking at something like a dashboard that's relatively large, I would probably choose flame in that situation, again, because I can cover the area much quicker than I can with a blown ion. But again, there are other applications where maybe the strength of the blown ion based on the surface that you're treating will be higher than the flame. So again, you just have to look at the material, you have to look at the dimensions of the material, you have to look at the speed in which you're operating and how often and how fast that you need to treat these. But there's a lot of different variables that you have to look at before you can decide on one application versus another.
All right. Greg, what is a good technology for bonding two substrates with different CTE, coefficient thermal expansion values?
That'll depend on the application. You have to keep in mind, obviously, that the CTEs are different. So if you do not need a super high structural bond, you might find that a silicone will provide a seal that is sufficient. So silicones are very good at dealing with differences in CTE values because they're very flexible. If you need a little more adhesion than that, you might want to look at a polyurethane because they tend to be a little softer and a little more flexible and can accommodate the differences in CTE values. Otherwise, you could look at some specialty epoxies that are softer. A hard epoxy will probably cause you some issues.
All right, we have a question here related to, is it practical to treat a carbon or glass fabric impregnated in an epoxy BMI cyanide ester? We often bond metallic components to a composite surface. Can that be plasma treated?
Yes, it can. Composites to metal is a common application, especially in aerospace. Composites are very easy to treat, most usually with a blown ion type system. You can also treat the metal side as well, but both of those will increase the surface energy and improve the bond. It's used in a number of aerospace applications right now. I was running a test Monday and Tuesday with an aerospace company, and we were doing composite bondings to metal structures.
All right. Here's a question on can it be quantified, the potential impact of bond strength on different surface roughnesses on an injection molded plastic part? This company has a part that currently comes off the tool with a smooth finish in the bond area, and they are considering making a tool change to add a texture.
You probably could do it within the framework of your specific part in your adhesive, but there's not going to be a generalized answer to this because it depends on the plastic that you're using. It also depends on the adhesive that you're using. So if you have materials that are not great with one another, you can texture it and actually see no improvement at all. In other cases, you could see quite a bit of an improvement.
Yeah, I agree completely. It may be effective to change the mold so that you get a little bit of variability there in the surface, but you also could use a flame or a blown ion probably and achieve the same results after the fact. So it just depends.
Wilson, a couple of people have a question related to what's the difference between corona treatment and plasma treatment?
I don't know. Well, I do, but plasma is blown ions. So again, I'm taking, if I'm using compressed air, I've got hydrogen, I've got oxygen, I've got nitrogen in there, and I'm taking the percentages there and changing them into ionized gas that's blowing onto the surface. Corona is more of an electrical stimulation of the surface. You can increase surface energy with corona as you can with plasma. The basic difference is that corona does not clean the surface. So, and it does not affect the surface roughness to the same level as blown ion does. So, a blown arc is a good application if you only need to, again, activate the surface for a short period of time. It doesn't last quite as long as a blown ion. So there's a lot of differences there, but the basic is you're not going to clean the surface with a corona. You're only going to activate the surface, and corona is a very, very short. It needs to be in line in a roll-to-roll type application in order to be effective. The time the treatment lasts is very short, and by short I mean seconds and minutes. So you couldn't treat a part with corona and then take it to another section and bond it effectively. You would need to do that immediately after the corona treatment.
Can you comment on how plasma treatment can be used to prevent adhesive failure due to surface migration?
Surface migration is tough. If you've got flame retardant material in there, you just have to run the test. Many times you can change the outermost molecular layer of the material so that you are able to still achieve good bonding. But if there is migration through the material, and again, I mentioned fluoropolymers because they are the worst, many times you just can't use a surface treatment like a blown ion or a blown arc or flame. The treatment is just too short, and again, after you've treated it, if there's migration in the surface, you're just gonna, the part that you treated is no longer on the surface anymore. So about the only sure way to do that is with some sort of vapor deposition on the surface, and that can be done with vacuum plasma or other methods. And then you are changing the outermost, again, you're putting a nano coating on the surface in that case that is not going to be affected by the migration.
Is there a Dyne or contact angle value that you would consider a threshold for good bonding, or does it vary based on material?
It varies based on material.
Are there any potential drawbacks or negative effects on the bonded material? I'm assuming this is related to after surface treating.
No. Generally, we're only affecting the outer 1 or 2 molecular layers, so we're not affecting the material. We're not affecting the material's strength. We're not durability or heat sensitivity. We're not affecting the material at all.
If an assembly is planned to be heat soaked before plasma treated and potting, which heating method would be best to prevent post-contamination?
Without testing, I honestly just don't know the answer to that. I apologize. Contact me after and let's get some more information, and maybe I can get a better job, but without testing, I just can't be sure.
Is ventilation required when using a blown ion system?
Yes, it is. You're creating NOx, nitric oxide, and various species. So we're putting, for a single blown ion jet, we're putting about 1 cubic foot per minute of air through there. So we recommend that you at least ventilate that much off. 70-something percent, 78% of air is nitrogen. So not all of that is turned into NOx, and by NOx I mean NO or NO1 or NO2, NO3. It's not a huge issue. If you breathe it for long enough, it will dry out your respiratory system and you will have a sore throat. But generally, you just need to vent that to the outside air.
All right. Looks like we are getting a little bit past our hour. We're going to try to get to 1 or 2 more questions here before we wrap things up. Will an increase in Dyne level also increase long-term performance at high temperatures as opposed to a single bond strength increase from a pull test? Is temperature cycle testing typically performed with any load applied?
I'm not sure I completely understand the question, so I'll take a shot at it. In terms of increasing the Dyne level and increasing performance at high temperatures, those are different things. So if you get a good bond at under ambient conditions and you needed the Dyne, you needed to treat the substrate in order to get that bond, it doesn't mean that the adhesive that you selected is actually a good choice for high service temperature situations. So you may not see a good bond at high temperatures that you did see under room temperature type situations. What was the rest of the question?
I don't, it's gone.
If you want to talk about that some more in detail, feel free to send me an email.
Yeah, you've got both of our presenters' phone numbers and email addresses there on the screen. Feel free to reach out to them as well. We're going to take one more question here. In the beginning of the presentation, it was mentioned that some adhesives are convenient for plastics bonding. When using these adhesives, is it also necessary to treat the surface? And if it is, what is the benefit of the treatment?
That's situation specific as well. You can frequently find adhesive materials that will bond to your plastics and give you an adequate bond, and you're fine without any kind of treatment at all. You know, as I said earlier, if you take, say, a solvent-borne adhesive, if that's something you actually can use in your application, they frequently will wet out substrates anyway, and they don't necessarily need as much help as, say, a waterborne adhesive, which tends to be more problematic, and then treatment might be more important.
I'll add one thing to that as far as an advantage of treatment. Many times we look at applications, and after you treat it, you may be able to use less adhesive to achieve the same bond strength, or you may actually be able to use a less aggressive adhesive, which generally means a less expensive adhesive, and get the same bond strength. So that's something to consider as well. I've seen applications where you were able to reduce the amount of adhesive by up to 40%. So if you're using a lot of adhesive and not using surface preparation, it might be a way to save on some cost of that adhesive.
All right. Thank you, Greg. Thank you, Wilson. And thank you to our audience today. We'll be processing this recording and getting it posted online. We will send everyone a link to the presentation slides as well as the recording. And again, we thank you for attending today, and we look forward to seeing you at our next webinar. This will conclude today's webinar. Thank you.